Okay, so for section 4.1, we are talking about higher order derivatives, and this will lead to a discussion about concavity. Um, so basically, we're moving on to the second derivative. We're going to take a derivative of our derivative. Um, so let's start by looking at these two graphs. Both of these, f prime is positive, right? The slopes of these tangent lines would all have a positive slope, right? So the difference in these graphs is that these guys, your tangent lines, these over here, sorry, these are getting less steep, but these are getting steeper. So this is F is increasing at an increasing rate. And on this one, F is increasing at a decreasing rate. It's still increasing, but it's increasing less the further you move. So the similarities and differences, F prime is positive for both. So, but the difference is that what we just talked about, that F is increasing at an increasing rate for the one on the left, and it's increasing at a decreasing rate on the right. So this is it's the slope of the slopes and how the slope of the slopes is changing, and this is going to bring in the second derivative. So I like to make a smile out of these and a frown out of these. So the function is concave up if the slope is increasing. So that's our first picture. This is the smile. And it's concave down if the slope is decreasing. And that is the second one where it looks like a frown. Yeah, so one way to talk about it is like, would the graph hold water? If so, it's concave up. If it would spill water, it's concave down. So like this right here would hold water. This is concave up, like a cup, like a cup. And this is concave down. Let's use a different color, red maybe. This is concave down like a frown. Frown. Okay. So we are going to talk about, this is concavity, concave up like a cup, concave down like a frown. What's going on with the second derivative, we'll determine this more about that as we go. So an inflection point is the point at which the graph, sorry, I got confused about my color choices there. An inflection point is the point in which the graph has a tangent line and the continuity changes. Oh. So in this graph above, that's supposed to be the concavity. This word is concavity. So this, on this one, let's use purple. The concavity actually changes right here. This is an inflection point. It switches from being concave down like a frown to being concave up right there. So that 0.00 is an inflection point on that graph. Okay, so we're going to do this with a couple different graphs. We're going to figure out concave up, concave down in inflection points. Let's see, up we're going with blue, down we're going with red. Okay, So I'm not sure if you can tell, but like here-ish and here-ish, um, this would be concave down like a frown in the middle here. And then these guys would be concave up like a cup. So we have concave up. That's going to happen from negative infinity up to, let's go with -1. And then we're going to union that with +1 to infinity. And this will be concave down like a frown in the middle there from -1 to 1. Your points of the points of inflection, sorry. Color those in purple. This is POI and this is a POI. At -1, -1, and 1, -1. All right, let's keep going. This one's kind of odd, but you have, I don't know if you can see this sort of like frowny face here. And then we would have sort of a cup situation going on over here. So our point of inflection here is this guy at 0, 0. It is concave down like a frown from 0 to infinity. And it appears to be concave up from -infinity to 0. All right. This one, we have the POI like here, point of inflection here, and we've got a sad face on this side, and we could probably hold water over here. So we have concave up from 0 to infinity, whoa, and concave down from -infinity to 0. We have a point of inflection or a place where it changes concavity there to 0, 0. All right. So we are going to now just practice before we actually try to use functions to figure out concavity. We're going to practice just taking second derivatives. Oh, we have one more example, sorry. Let's see. This example we have, it looks like we have a POI like here maybe, and perhaps right here. And it looks like in between those, we have a frown situation, and on the ends, we have a cup. So we have concave up from -infinity to -2, and from 0 to infinity. And we have concave down from -2 to 0. And then our points of inflection are at -2, 2, and 0, 0. Okay, so our definition of concave up is that the slope of f prime is increasing, and slope is given by f prime of x. So what does concave up tell us about f prime of x? That the derivative of f prime is positive, right? If f prime is positive, that means f is increasing. F prime positive means that f is increasing. F double prime positive means that f prime is increasing. These actually go both ways. So So this is what the derivative of f prime is positive. That tells us that if the derivative of f prime is positive, then f double prime is, then f is increasing. Slope is increasing, that means the derivative of f prime is positive. Oh, I've used this double tick mark. That's a second derivative, but we haven't defined that yet. I will in just a second. The derivative of f prime is positive. The graph being concave down says that the slope is decreasing. The derivative of f prime is negative. Okay. The second derivative is often going to be use this notation. That's those two tick marks for 1, 2 derivatives. You might see, d by dx of f prime of x, or this is my least favorite, but people do this d2f, so the second derivative of f with respect to x twice. This would be more important in like a Cal 2, Cal 3 class, but for us, this is pretty good. So the graph of f is concave up if f double prime is positive. It is concave down if f double prime is negative. Okay, we're going to apply this stuff in a minute, I promise, and this will make more sense, hopefully. But for now, as I was saying before, we're just going to take a bunch of second derivatives to make sure we can, and then we'll use it to talk about concavity for certain functions. So f prime here, we're going to do the power rule several times. So negative 3x squared plus 4x minus 3 plus 0. And then f double prime, you're just going to take another derivative. Same thing, doesn't matter. Just like ignore that this is f prime. Just take another derivative. So negative 6x plus 4 plus 0. And do that again. G prime here would be exponent down from, we get positive 12x to the negative 3 minus 12 times 3 is 36, x to the negative 4. And then do another derivative. So G double prime, that would be negative 36, x to the negative 4. Plus, what's 36 times 4? 144. 36 times 4 is 24. That's 12, 13, 14, 144 x to the negative 5. Okay. Y prime here would be 3x squared minus 24 times 1/3 of x to the negative 2/3. I'm going to simplify that to make my life easier for taking a second derivative here. That's 8x to the negative 2/3. That's y prime. Y double prime would be 6x minus 8 times the negative 2/3 times x to the negative 2 minus 3 is 5. Negative 5/3. And then 16. So 6x plus 16 over 3 x to the negative 5/3. You don't have to simplify, I don't think. Actually, I know you don't. So leave it like this is fine. For taking a second derivative, once you have the first derivative though, it would be helpful to simplify it as much as you can before you take another one, because they're just going to get messier if you don't. All right, woo, this is going to be interesting. So y prime here is going to require a chain rule. So exponent down front, decrease it by 1, leave the inside alone, times the derivative of what's inside, which in this case would be 2x. So I'm going to rewrite that as 10x times x squared minus 16 to the 4th. And now I need to do a second derivative, which is going to require a product rule and a chain rule. So this would be like, this is f and this is g. It would be f first function times the derivative of the second plus the second times the derivative of the first. So we would have first function times the derivative of the second, which would be 4x squared minus 16 cubed. So exponent down front decreases by 1, leave the inside alone, times the derivative of what's inside. Plus the second function, x squared minus 16 to the 4th, times the derivative of the first. Okay. You could have done this, sorry, I was looking at my notes. You could have done this with this as your like f function and this as your g function. That's what I did in my notes, but it does not matter. It should give you the same thing. I'm just verifying that. Yes, yeah, it does. Okay. And now for one that would use the quotient rule, let's call this one y. So have y prime would be ho d high minus high d ho all over ho ho. That is x plus 5 minus x plus 3 on the top, x plus 5 squared on the bottom. I'm simplifying only because I'm going to have to take another derivative. That's 8 over x plus 5 squared. Oh, this is nice. That's good. Because we can write this as y prime equals 8 times x plus 5 to the negative 2 and take another derivative. So exponent down front would make that negative 16, decrease it by 1, then times the derivative of what's inside. Okay, so that's taking a bunch of second derivatives, and now we want to actually use that to do the concavity. So how can we use the second derivative to find intervals of concave up and concave down? We're going to use an f prime number line, a double prime number line. Remember the first derivative test, we used an f prime number line to tell us where f was increasing and decreasing. Now we're going to use an f double prime because this will tell us where f prime is increasing or decreasing. Will tell us where f prime is increasing or decreasing. Okay. The critical values, the CVs of f double prime are actually points of inflection. And we're going to find f double prime, solve f double prime equals 0, and then use f double prime number line to get concavity. Okay, so let's do this with some practice problems. So we have here we need to find the second derivative. So f prime, the directions to find the intervals of concave up and concave down. F prime here would be 4x cubed plus 6. F double prime would be 12x squared plus 0. That's so we're looking for critical values now of f double prime, which are going to be points of inflection. So we have x squared equals 0, divide both sides by 12. So x is 0. So we are going to put that on a number line, an f double prime number line. And we'll put 0 right here. And then we're going to test values just like we did before. So -1 and 1, but now we're testing into f double prime of -1. We make this 12 times -1 squared, which is 12. So that's positive. And f double prime of 1 would be 12 times 1 squared, which is 12, which is also positive. So this is concave up everywhere. All right. Let's look at what that looks like in Desmos. X to the 4th plus 6x. Yeah, just looks like a parabola. It's x to the 4th, so it could have a bunch of other, like an additional hump, which would happen like maybe in like this region around 1, but this one doesn't have one. So that's good. Concave up everywhere. Okay, number 2, we have x cubed minus 3x squared plus 7. So f prime of x is 3x squared minus 6x plus 7 plus 0, my bad. And then f double prime of x is 6x minus 6. So we're going to set this equal to 0 and solve. Okay, so x equals 1. And so we're going to put that on an f double prime number line and then plug stuff in. So say 0 and 2. So f double prime of 0 would be 6 times 0 minus 6. That's -6, which is negative. F double prime of 2 would be 6 times 2 minus 6, which would be 6, which is positive. So we have, this is concave down like a frown. This is concave up like a cup. Let's see. Concave down like a frown from negative infinity. Whoa, whoa, whoa. Negative infinity to -1. Concave up like a cup from 1 to infinity. And we have a POI at 1 something. This is f of 1, which is 1 cubed minus 3 times 1 plus 7. So 1 minus 3 is -2 plus 7 is 5. All right, so your POI happens at your x value, and then plug that into the original function. Okay, let's see what that one looks like. X cubed minus 3x squared plus 7. Okay, so it looks like we have, maybe that's at 1, 1, 5 is our point of inflection there. It's concave down until that point, and then concave up after that. Okay. Okay. Number 3. We are going to take a derivative and another one, 2 times 1/2 times x to the -1/2. Those cancel. F double prime of x be 6x minus 1/2 x to the -3/2. Okay, So this is the same thing as, let me leave myself some space here. So this is 6x minus 1 over 2 times the cubed root, no, the square root of x cubed as a 2 times the square root of x cubed. So because of that, this green, this square root means that x has to be positive because we can't take the square root of a negative there. So x is restricted to 0 to infinity. And then what we would do is, goodness gracious, set this equal to 0 and solve. Blue's fine. So 1 over 2 times the square root of x cubed equals 6x. And then I'm going to, actually, this is 1/2 times x to the negative 3/2. I'm going to multiply both sides by x to the negative 2/3. Oh. So on this side, those cancel and we have a 1/2 that's left. On the other side, I have a 1 and a negative 2/3. I would add those. I have 6 times x to the 1/3. Trying to make sure I'm doing this right. I think so. Okay, and then I divide by 6. I have 1/12 equals the cubed root of x. So if I cube that, I have 1/12 cubed equals x. I'm not sure about this. When my answers don't match my work, it starts getting to me. I worked this already, but I have a different answer now that we're doing this in the video, which is not all that helpful. Let's turn that off. I don't want those on there anymore. Oh my. Well, there is a little bit of concave down. Let's see, what can we call this? This is f of x. We can repair. No, that's not quite right, is it? Maybe. No. No, that's not right. Pause. Okay, I'm gonna fix this. I figured out what I did. Don't multiply by x to the negative 2/3 because this is like this, the 2 over the square root of x. We're gonna sorry, the square root of x cubed, that's on the bottom, so we're going to multiply it on the top. So multiply x to the 3/2. And then we would add, and those things would go to 0 when you add. That's how this works. Excuse me. And then 1 and 3/2 would give you 3, 4, 5/2. So we have 6 equals the 5th root of x. No, the square root of x to the 5th. 1/12 equals x to the 5/2, or let's write it as x to the 5/2. X to the 5/2, and then we need to get x by itself, so raise each side to the 2/5 power. Here we go. 1/12 to the 2/5. Gosh, is x. Yikes. 1/12 to the 2/5 power. Let's see what that looks like in Desmos. 1/12 to the, oh, good. That is that point. That's great. Okay, so there's your 1/12 to the 2/5 power, and that does look like it's the right spot for the concavity switching. So 0.371 is that decimal. So we'll go with plugging in 0.25 and then 1. This is an F double prime number line looking at concavity. So F double prime of, sorry, this should be an orange. F double prime of 0.25 is something negative. I have negative 2.5. And F double prime of 1 is 5.5, which is positive. So we have concave down from 0 to 1/12 to the 2/5, and then concave up from that number, 1/12 to the 2/5, to infinity. And we have a POI at 1/12 to the 2/5, and then whatever that F value is there. Which I did not figure out, so we'll just write F of that. Use a calculator and figure that out. But there is that. Oh wait, it's on here. We have it here. It's 6.267. All right. Ooh. Okay, let's do these last. Let's actually just do, yeah, we should do both of these examples. All right, F prime here of x is going to be exponent down front. Decrease it by 1. That's 1/3, so negative 2/3 times the derivative of the inside. So we're looking at 5/3 times 5x minus 3 to the negative 2/3. And we're going to take another derivative. So exponent down front would make this negative 10/9 because you would multiply 2/3 and 5/3. Negative 10/9 times 5x minus 3 to the negative 5/3 times 5. So this is equal to negative 50 over 9 times 5x minus 3 to the 5/3. All right. This is going to work. Let's see if I can move that out of the way here. There we go. Put a line here. Okay, didn't mean to put it on top of there. put it right there. Okay. So then we want to, for the zeros, which in this case it doesn't have any because of this guy, this is, the top's not zeros, so the top has no x's in it, so it can't be 0. But it is undefined anywhere. But it is undefined at 3/5. That would be the 0 of this guy. What would make that 0? So we're going to use that in our number line, our f double prime number line. 3/5. We'll plug in 0 and 1. F double prime of 0 I have is positive. F double prime of 1 I have is negative. You might want to check that in a calculator, but that's what I have. So concave up, down, sorry, we'll do that in red. Concave down from 3/5 to infinity. Concave up like a cup from negative infinity to 3/5. You've got a POI there at 3/5, and then f of 3/5, which is 0. You plug in 3/5 here, you get the cubed root of 0, so it's 0. Okay. Last example for this video, and then I will start another video to talk about the second derivative test. Let's finish this example first. So we have f prime of x. I'm going to use a quotient rule. So ho d high, so 1 minus high d ho all over ho ho. Ugh, I have to take another derivative of this mess. That's x squared minus 4 minus 2x squared on the top. So simplifying, that gives me negative x squared minus 4 on the top and x squared minus 4 on the bottom squared. So the second derivative would be ho d high minus high d ho to x squared minus 4 to the first times 2x. Holy. All over ho ho. Well, that is something. Ooh, okay, let's see. All right. Okay, I see this and this and this. There are 2 of these, 1 of these, and 4 of these. I'm going to take 1 out of all of those pieces. Basically think about it like factoring that out and then canceling it. So there would be 1 left there times that negative 2x plus, I'm going to distribute that negative x squared plus 4. And then here there was 1, so now there's not any left, and this is just 2 times 2x. And then on the bottom, it would be cubed now because we took 1 away. Okay, so On top, we have negative 2x squared plus 8x plus x squared. No, that's 4x times x squared, so 4x cubed plus 4 times 4 is 16x. X squared minus 4 times the cubed. Everything's going off the rails. Oh, this is cubed. Okay, so on the top, goodness gracious, I don't have room to do all this. On the top, we have 2x cubed plus 24x. On the bottom, x squared minus 4 cubed. So we have, goodness gracious, this is f double prime of x. This has, where the top would be 0, x squared plus 12. That's where the top could be 0, and the bottom equal to 0 would be at 2 and negative 2. So we put all three of those on our f double prime number line. Put negative 2, 0, and 2. Where the top is 0 is where the whole thing would be 0. Where the bottom is 0 is where it would be undefined. So those are the three potential points of inflection for us. Then we would plug in some test values. So negative 3, negative 1, 1, and 3 maybe. And when you do that, golly, f double prime at negative 3, f double prime at negative 1, f double prime at 1, and f double prime at 3. That goes negative, positive, negative, positive, negative, positive. So negative, positive, negative, positive. Use your calculators to do that. Okay, so we have concave down on those and concave up here and here. And since negative 2 and 2 are, it's not defined, they cannot be points of inflection because they're not even on the graph, but this is our only POI. The same reason that like a place where the function isn't defined can't be like a min or a max, that a place where the function is not defined can't be a point of inflection either. So the 0, whatever f of 0 is, would give you your POI, which is 0. All right, I'm going to stop this video. I will pick back up here at this. Actually, let's just finish this. The concavity at a local max. So if you look in at this local maximum, the concavity is concave down like a frown. And if you look at a local minimum, it's concave up like a cup. I should fill that with water. A smile. So that's going to lead us into talking about the second derivative test, which we will do in the next video. Thank you so much.